Today we have Anna Rechtman from IMATE, the University of Strasbourg. Who's going to speak about dynamics and topology of the minimal set of Kuperberg's law.
Well, thank you, and thank you, Alberto. I started doing mathematics here 10 years ago or so, in Alberto, and then moved to France, where I'm now. So I will speak a little bit about the minimal set of the Kuperberg block. This is a joint work with Stephen Herder. It's a work in progress. I will tell you some aspects of the study we have done in the last few years. So I will start by telling you what Kuperberg proved and how she proved it, and then go into the details of the minimal set and what it is. So what Christina Kuperberg block is proof is that if you have a closed tree manifold, you can it always admits a non-singular vector field without periodic orbits. So the first remark is that a tree manifold has always Euler characteristic 0, so it always has a non-singular vector field. And the idea of the proof is that if you start with a field that has a finite number of periodic orbits, you can change it for one without periodic orbits. So if, let's say, I have a periodic orbit, the idea is to do a local construction. So I will choose a point, and around that point I can choose a flow box. And the idea of Christina is to change the vector field inside that box in order that I will cut open the periodic orbit. On your left, you have a flow box, which just you have vertical vector field, so it's going up. And what we want to do is to change the interior. So what I will do is erase the flow inside the flow box and put another one. Okay, so this is not Christina's, it's just an idea. So what do you need to be able to do that? Well, the first thing you need is that the vector field has to be vertical near the boundary. So I can paste. Okay, so in a plot, the vector field will always be vertical near the boundary of the plot. The other thing you want is to have trapped orbits. So an orbit like the blue one, so it will come in, and then we'll start turning around inside the plot, but will never go out of the plot. Okay? So this will allow us to trap this periodic orbit, and so it will stay inside the plot, it will never become periodic.
Isn't it good to say you also want the vector to be transversal to the top and the bottom?
Yeah. So when I say vertical near the boundary, I also say top and the bottom.
Also good to say.
Yeah. And the other thing you want is the entry-exit condition. And this is a very important condition. So the entry-exit. So let me tell you what it is.
Substance.
So you want to be able to control the orbits that go through. Okay? So if an orbit comes in, well, if it's near the boundary, I know it's vertical. If it's trapped, it stays inside. But there are orbits that maybe will do complicated things inside and go out at one point. But what you want is that the point that goes out is just in front of the point where it came in. So that way, if you had a periodic orbit, it will stay periodic. It may get longer, but it will stay periodic. If it was not periodic, it will stay no periodic. So you can control what's happening. Okay, so these are the basic.
You go out the same place you come in.
You go out at the same place you come in. You may do a complicated
or you
thing
don't go
inside,
out at all.
Or you don't go out at all. But if you go out, then you go out exactly in front.
And then you are allowed to destroy the periodic orbit.
Yeah, because I have trap points. And this, I will put them in a periodic orbit. Okay? So here is accumulating a periodic orbit. The idea of Kuperberg is to have a plug that has no periodic orbits inside. So when you cut the periodic orbit, you are not creating new ones. Okay? So Christina Kuperberg constructed a plug without periodic orbits. And one important thing for my talk is that a plug is also an instrument to introduce a minimal set into a flow. Because a plug has always a minimal set. So by minimal set, I'm saying a set that is closed, invariant, that doesn't contain any proper subset that is closed and invariant. And so if you have a trapped orbit, it will go and accumulate on some invariant set that will contain a minimal set. Okay? So let me tell you a little bit of
Minimal set means a minimal closed invariant set.
a minimal closed invariant set. Yeah, that's what I mean. So let me tell you a little bit about the history of this theorem, what happened before. So in the 50s, Seifert proved that if you have a vector field that is C0 close to the half vector field, so the vector field that is tangent to the half vibration, then it always has periodic orbits. And it asks whether this is true for any flow on the tree sphere. So if you get a non-similar vector field on the tree sphere, thus it has a periodic orbit. And the positive answer to this question became known as the Seifert conjecture. And this is what was disproved by Christina Kuperberg. Then in the 60s, Wilson constructed a flow with finite number of periodic orbits. So actually 2. That's an Alberto remark that the Wilson construction gives you a flow with only 2 periodic orbits. And that's why I can say I can start with a flow when I'm with Christina's construction. I can start with a flow with a finite number of periodic orbits. Okay, this construction is already done with plugs. So Wilson introduced plugs to this study. He also proved that the Seifert conjecture does not hold in higher dimensions. So his plug, the periodic orbits of his plug can be replaced by tori with an irrational vector field. So that in higher dimensions, if you have a manifold with a flow without fixed points, you can always change it for one without periodic orbits. So he kind of answered the question in higher dimensions, not in dimension 3. And then in the 70s, Paul Schweitzer realized that you can change these periodic orbits in the Wilson plug for the minimal set of the Donjoy flow on the torus. Okay? So this gives you examples without periodic orbits, but the Donjoy vector field is just of class C1.
Well, 1.9999.
Yeah. And then Jenny Harrison did a huge amount of work to make this example C2 by putting the Donjoy flow in a fractal way inside of it. Okay? So what I want to stress a little bit is here, so in the Wilson plug, the minimal sets are the periodic orbits. Here is, well, 2 copies of the Donjoy minimal set on the torus. And what I want to say before passing to Kuperberg's construction is that these constructions come from the minimal set. So in Schweitzer's, for example, you start with the minimal set, and then you construct the plug around it. And in Christina's completely different. Okay, so let me...
Can hers contain these kind of minimal sets?
No.
There's a obstruction.
Yeah.
Some smoothness obstruction.
Yeah, there's a smoothness construction, yeah. So this is what we're called after. So there's a paper, maybe I will just say it briefly. There's a paper between Schweitzer's construction and Christina by Michael Handel, where he proves that if you have an isolated minimal set, but by saying that there's no bigger invariant set, then it has to be surface-like. So it has to be a Donjoy, basically, and then you cannot have it. It has to live on a surface, maybe with contact. Okay, so let me pass to Christina's constructions. So we start with a very simple vector field in a rectangle. This is just a vertical vector field. So in the middle line, I want to have 2 singularities. And what I want, the only condition I ask is that it's antisymmetric with respect to the middle horizontal line. That's the only condition I ask for the moment. And now what we're going to do is to multiply this rectangle by a square. So we obtain dots it looks more or less like this. And inside I want to put a vector field, and the vector field is going to be W1 plus a function d on x. So this function is defined on the rectangle if it has values from minus 1, 1.
Wait, I understand. What's the notation? What are you talking about?
So I want to put a vector field here. The vector field will be the vector field I have in the rectangle
Oh,
plus
W1.
F d on dt. Okay? So F is a function that depends only on the coordinates of the rectangle, doesn't depend on theta, and has values on minus 1, 1, let's say. So what I want to ask in this function is to be positive, to be equal to 1 on P, to be equal to minus 1 on Q, to be 0 near the boundary, and to be also antisymmetric with respect to the middle line. Okay, so what's happening in the plot? So the first singularity over there gives me a periodic orbit that is turning in the positive direction. And the second singularity over there gives me another periodic orbit that is turning in the other direction. Okay? So since I put F equal to 0 near the boundary, the vector field is vertical near the boundary. So it comes in vertically, it goes out. Okay, so this is the entry region, this is the exit region of the plot. And then the points, for example, if I take a point that has radial coordinate equal to 2, so the W1 just goes vertically to the singularity. So what happened here, take a point with R equal 2, it will start going up and then turning and accumulate on the first period. So this will be my trapped points. And then the other points, I don't know, if I take a point here,
Wait, you said which coordinate did you take?
R equal 2. So this coordinate
middle.
equal to the middle line.
Just that one.
Just that one. It's a circle that is trapped. Okay? And then since I took everything antisymmetric, what's happening with a point here? Well, first it starts going up because I'm near the boundary. And then I will start to have a positive F if I'm near the periodic orbit. So we'll start going around. But always climbing, because W1 vector field is always positive. So at one point I will get to the middle line in the rectangle where F is equal to 0. So here I'm vertical. And so there is vertical, and then it will start turning around in the other direction. And it will do exactly the same path it did in the bottom half of the plot. So it will go out exactly in front of where it goes. Okay? So this is what we will use, and what is important here is that the vertical lines, so the cylinders where my coordinate R is constant, these are invariant. And in these cylinders, more or less what we have is this flow lines. So near the boundary, it's almost vertical, and as I get to the middle of the plot, things start to turn around, as I told you, this red orbit, so I turn around and they go to the middle where it's vertical, and they turn back around to go out in front. And when I get to R equal 2, I have my two periodic orbits, and in the middle I have a cylinder, an invariant cylinder, and I will call the rep cylinder, and will be important in what follows. So now it comes the great of Christina's Kuperberg is to kill these two periodic orbits. So how do you kill these two periodic orbits? And the idea is to trap the periodic orbits with the same block. So we will do some outer insertions of the block in itself.
The idea is to what?
To kill the periodic orbits with the same block. So we will take parts of the block, insert it in itself, to trap the periodic orbits in the same block. So the first thing, so this is easy, I will just take the Wilson block and embed it as a folded 8 into R3, preserving the vertical direction. Okay? And now we will start pulling horns, let's say. So I will go a little bit fast at this point. You can just slow me down if you have questions. The idea is to bring these pieces inside the block to trap the periodic orbit. So let me put the final picture of the plug and then spend a little bit of time explaining you this. Okay? So here are the horns that came in. Okay? So we're doing two auto insertions of the plug. Or out inserting part of the plug in itself. So how we do that? So I go to the Wilson. And here we'll choose. So when I grew horns, it comes like to choosing some disk on the entrance of the plug. So each horn will be this. I will do it for one. The other one is analogous. So I choose a disk. Okay. So how I choose a disk? Well, I want to have at least one point with r equals 2. So I will, if this is the circle r equals 2, I want my disk to have some arc in there. And I will mark an inner point in this. Okay, so this is what I choose. Now this red arc boundary of my disk, I will map it to the boundary, inside boundary of the Wilson plug. Okay? So I'm just mapping the disk for the moment.
What properties of the Wilson plug do we have in our mind to follow what you're talking about?
The invariant cylinders.
Huh?
The invariant cylinders. Just invariant cylinders. That's what you have to keep in mind. And the fact that you have a periodic orbit, two periodic orbits.
Very.
Cylinders.
Two previous.
You kind of introduced the name Wilson plug kind of in the middle of your discussion, so I got lost. You were talking about Kuperberg plug before.
So I have the Wilson plug, and I will do
But
insertions
we don't have
to
the Wilson
obtain.
plug in the lecture. We
This
don't
was
have it.
the Wilson plug. This was
Where?
the-
What's the
This is a
Wilson plug?
This is Wilson.
Oh, W1 is Wilson plug. W.
Away from Wilson.
Oh, okay, fine. Okay.
This
I
is
see.
my Wilson plug that I will
Okay.
use. Okay, so I will always call it the Wilson plug.
Okay.
And what I want to do is to use it to produce the Kuperberg plug. So what I'm saying is the auto insertions, how they're constructed. So first I just choose a disk in the entrance. It's the first thing I do. And then this red arc, I will map it to some arc in the inner boundary of the Wilson. So it comes to choose some other arc in this inner boundary. Okay? And then I want this disk to be transverse to the flow, and that the special point I choose will get mapped to the point in the periodic orbit. Okay? So what this has to do? Well, it has to go into the plug, it has to climb to get to the periodic orbit, but it also has to turn because it has to be transverse to the flow, and the flow here is horizontal. Okay, so the disk comes in and then it turns to become transverse to the periodic orbit. So
You're just saying do that picture.
yeah, I'm describing how you do this picture.
Okay, you just do it and you just imagine doing it.
Yeah.
Okay, fine.
And then once you embed the disk, you can push it with the flow and create some region where instead of just embedding the disk, I will embed the disk from my vertical. So what I will do is first I push the disk, I create this region where I will embed this part. I will erase the flow in it and put the flow that I'm bringing with embedding.
Now, why is it going around twice like that? What's that's supposed to suggest to me?
So that's because I want the outer boundary of the Wilson to be in front of the inner.
To be what?
In front of the inner boundary. I mean, so I can do this.
Ah.
Not how you get to the boundary of the flow. That's why you do this double.
Another thing is no longer homomorphic to square cross.
No, it's not. But so the important thing, so this is a plug. I mean, the important thing, so what I said, what I wanted to prove, so to be a plug, I wanted to be vertical near the boundary. I didn't change the flow near the boundary, so it's still being vertical. And then, well, we have to prove the entry-exit condition. It has to be proved. And the other thing is that this plug has no periodic orbits. So there's one condition. So this is how the flow looks inside the insertions. First another picture. And there's one condition in the construction that we need to prove the periodicity. So let me explain you this construction. So if you come back to Wilson and you take a small transversal around the point of the periodic orbit, and you push this transversal, so you have the middle point, the center point, that is your periodic point, and then you see the invariant cylinders. So these are just invariant cylinders which you're pushing. When you get to the insertion, you will see another cylinders coming in, but this time will be, you're getting to the Wilson plug from the bottom, let's say. So you will see these curves described by the new radius. Okay? So we wanted, so I choose this special point to go into the periodic orbit, so at that point I want the radius not to change. And what it says, the radius inequality, is that for any other point, the radius will grow when you go into insertion. So this is a monotonicity condition that allows to prove that the plug has no periodic orbits and that the entry condition is satisfied. Okay, so this is the main radius inequality. I won't go into the proofs that this has the entry exit condition, that this has no periodic orbits. There's at least 3 papers with this proof that contain these proofs. I want just to say something before passing to the next thing, is that we can choose a lot of things here in these constructions. We can choose the vertical vector field and the function in the construction of Wilson, but we can also choose how these curves look like. I mean, it could be any curve that satisfies that inequality will give you a Kuperberg plug without periodic orbits. So it's actually a lot of examples inside.
Does it still have to have a
So you
tangency
don't.
like that?
You don't.
No?
You don't. You can do more wild things. But so at one point I will assume that these are parabolic, that have parabolic shape at one point in the, I will say that. Okay? So it doesn't affect the fact that the plug is aperiodic, but it will affect the minimal set.
If there's a real analytic example?
There is a real analytic example. I'm talking about the sensitive example now. This is a comment of the TNGs that you can do it analytically. You have to be very careful on the boundary that you can do it. So let me tell you a little bit of the dynamics of this plug. So this is the Wilson plug, okay? Where I erased what is inside of the insertion. So this is the region where the insertions are performed, and the disk plus an interval that are behind, these are the regions that you will insert. So this is, I don't know, you can call it in different ways, but this has all the information of the Kuperberg plug. If you identify, for example, this entry region of the insertion with the disk that is here behind, and the exit with the top disk, and the same with the center. So what I want to say with this picture is that whenever you follow...
Did you say that again, that the dynamics is determined by what data?
So the data is, this is the Wilson plot where I erase some parts, and the data is, I identify this disk in the entrance.
Which disk is that?
So the entrance here, up here, with this one. This is the insertion I did, and I mapped that disk into so this disk is mapped into this one. The one that comes from the top and goes to the exit is the top one. And then here you have another one that goes up here into the second periodic orbit. It's identified with this one.
Okay.
And the top with the exit. Okay? So we'll call these disks, these 2 disks, the secondary entries. So these are the regions where I got into an insertion, and the exit ones, the secondary exit. Okay? So here you have all the information you need to understand the Kuperberg. Because when you follow a flow line on Kuperberg, it might not intersect the insertions. Well, if it doesn't intersect the insertions, it's just a Wilson orbit. Nothing changed. If it intersects the insertion, then it gets chopped into arcs, and these arcs are part of Wilson orbits, the ones that survive from the Wilson productive spectrum. Okay? So we will use, so in all the studies of this plug, we use the coordinates of the Wilson plug. They are not longer continuous along the flow, but you jump when you go into an insertion and out of the insertion, etc. And well, I will say that an entry point is facing the exit points if it has the same r and theta coordinates. So it means, like here, these 2 points are facing, but it can also be in the secondary entries and secondary exits. And the main lemma to understand how the orbits behave is this. So suppose you have an entry point that has radius bigger than 2. So either, let's say, a principal entry point or a point in one of these insertions that has radius bigger than 2. So if this is inserted radius equal to 2, well, you're thinking of a point that maybe is here. So when you're in a point in an entry, in a secondary entry, you have a radius before and a radius after. I'm thinking of the radius that is after. Okay? So if this radius is bigger than 2, the orbit will go to the facing point. And it will do maybe a very complicated path, but at some point it will get out of the insertion exactly in the facing point. Okay? And more than that, it will contain all the Wilson arcs of the orbits that survive, by meaning that all the arcs of the orbit of X are in this point. Okay? So for example, if you take this point and you follow it. So I'm starting with a point that has radius bigger than 2. Okay? It will go and intersect the insertion. So I'm not saying what is going to happen then, but at some time, maybe long, I will go to the point facing it. And then I will continue in the same Wilson orbit that I started with. And I will continue going up and turning again, and maybe hitting the insertion again, and doing the same thing. As long as the radius is bigger than 2. And so, for example, this point will eventually go out. And this is how you prove the anti-exit condition, how you prove the free list. So, now let me pass to the minimal set. So the minimal set, so it was already known before our study that there's just one minimal set inside of one. The minimal set is given by the closure of any of these 2 special orbits. So the special orbits I'm calling the orbits that were the periodic orbits, so that form the arcs of the periodic orbits that survive the construction. And if you take, so what I want to show is that if you take the closure of the first special orbit, it's equal to the closure of the second special
In what order should I follow the red axis? Top, bottom?
I will go to that.
Mhm.
So I will prove that. I will not prove that this is the only minimal set, because I need much more information to tell you that. And I will also prove that this contains points of the rep cylinder. That this closure contains points of this rep cylinder that was between the 2 periodic orbits. Okay? So let me start with the first special orbit, so the green arc. So this is the cylinder R equal 2 in Wilson, where I erase what's happening inside the insertion. Okay? So this arc comes into the insertion and hits the first insertion. And it hits this, and this is a special point I choose that has radius equal to 2. So by identification, I find myself in a point, in an entry point, that is this one, etc. That is in this cylinder. And now I start going up. So it starts going up, it turns, and eventually hits insertion. Because I'm getting close to the special orbit, so I would hit insertion. But at that point, the radius inequality tells me I'm hitting in a point that has radius bigger than 2. So I don't know what will happen then, but eventually this orbit will go out just in front. And then it will continue the same Wilson orbit, turning around, hitting the insertion again, doing some blah blah blah, then going out in front, continuing turning around.
But it goes out a little bit off.
Yeah, it goes up every single time. So I just put one. It goes up every time, but it's bounded by this one. Because the Wilson orbit is accumulated in the periodic orbit, so I'm just bound. Okay? This is what happens in cylinder R equal to. If you follow it backwards, well, I'm finding myself in an exit point of Wilson that is facing, so in the facing point here, and then I will start going back and eventually hit the insertion in an exit point, again with radius bigger than 2, and so I know I will continue turning back. So in the backward direction, I will accumulate on this red arc that is here. And the red orbit does exactly the same. The forward direction, it will go and accumulate on the first horizontal arc, and the backward direction will go and accumulate on the second horizontal arc. So this means that the closure of these two special orbits is the same. And now what I want to tell you is why this closure contains points of the Roth system. So instead of looking at this picture where I want to look, it's a small transversal in the entrance, the entrance of the first insertion. If this is this picture, I have my vertical radius equal to 2, the inserted radius. This is my special point. Okay? So when I construct it, as you told me, these points are going up, but they're bounded by this one. They're accumulating on the first one. So I have a sequence of green dots that are accumulating on the top one. Okay? So these are entry points, secondary entry points that have radius bigger than 2. And by my lemma, they don't go facing, they also contain all the Wilson arcs that survive. In particular, they contain the arcs that are at level C equals 0, the middle arc. So what's happening at there is that if you think, so this analog in Wilson, so C equals 0, I will put, this is the rev cylinder, the trace of the rev cylinder.
But you used to call the invariant cylinder.
Yeah, you can call it the invariant cylinder. So you have to think that the flow is coming out of the blackboard here, always. And so this green dots will correspond to, I don't have green, but let's put in red, to dots, points, each one will give me a point in this annulus that are each time closer to my cylinder. Okay? So it will accumulate in the cylinders and the closure will contain points of the cylinder. So this can be either a Cantor set or be dense. And here is where the parabolic shape comes. So what we prove is that if you choose everything to be quadratic, so by this I'm saying how the vertical vector field vanishes on the singularities and how the radius, this image of the radius is parabolic, then it will be dense. Okay? There were already examples of this. There's an example of a TNGs that tells you another genericity that's contained in this one, another condition that will give you density on the cylinder. And there's let's say an specific example where they do the computation in Rex Kuperberg and Christina Kuperberg's paper. So from now on, I will assume this condition. I will work with this condition saying that the minimal set has topological dimension 2. If it doesn't, then it's a set with topological dimension equal to 1 that is contained on this bigger invariant set that we will study. And so I will study the topology of this set. So let me tell you something. I haven't been able to construct an example, a specific example where the minimal set is topological dimension 1. I've tried, but I can't.
I thought you said it had 2.
Yeah, generically has 2.
Generic, oh.
But you could have, a priori you could have, I don't know any explicit example, but a priori you could have. So the proof before, it has a lot of estimates on how these points are distributed. It's much more technical. So let me study this rough cylinder, and for that I will go back.
The red cylinder ends up being really a cylinder.
No. No, because if it was a cylinder, if it was really a cylinder, then the
Yeah,
boundary will be periodic orbits.
That's right. That's right.
So it's not. But I call it the rough cylinder also.
So what do you think it looks like? Just
Well,
the,
we'll
the
tell you.
Disney example, the Disney explanations.
Yeah, that's what I will tell for the rest of how it looks. So first I have to go back to
There's an
Wilson.
idea here why it might not ever exist. The one, thin recurrence is generic. You can always open up things to destroy recurrence, and so it's generic to be smaller. So maybe it's some argument.
Yeah, I think there's some general argument behind this two-dimensional thing that we haven't
Okay.
found.
But there's this idea you can destroy recurrence.
Yeah, but
generically.
if you just, so here, the thing is that this recurrence is giving, I don't know how you put space into those things in this particular example. It seems that if you put
Oh, I
space,
see.
you will create periodic
I
orbits.
see, right.
Given
It's generic in a big space,
Yeah.
but not in your space.
Exactly.
Okay.
If I stay in the flows without periodic orbits, it doesn't seem that we can put space into it. So I think there's some general theorem saying that if there are no nearby periodic orbits, it's always a dimension. But I haven't.
If they're what?
If there are no nearby periodic orbits, not allowing this process that you're describing, then you can prove that some minimal set with some conditions on elimination has to have topological relations. Okay, so some kind of Dondron theorem,
Yeah, okay.
but that's just a dream of what we do. So let me go back to Wilson and think on the endpoint. So this is the bottom of the Wilson orbit. And let me mark the R equal to 2. Okay? So what I want to do first, before telling you what this set looks like, is to take a curve that is contained on the part that is not trapped and flow it inside Wilson. Well, what you get is some kind of surface. Okay? So imagine here is my small curve that I put there. So the boundary point goes boom, in front. It goes vertical. And the inside point will go around and then eventually will get vertical and go backwards. Okay, so this surface is as if you take just a rectangle on top of that curve. Take the middle point and start turning it around the red zone. Okay, so it's just a long ellipse that we call a propeller. And if you think of how the flow lines look on this surface, well, there's a boundary one, and then as closer you get, farther you go on this surface. And this one we'll call a propeller, so this is what we call a finite propeller. And then you get this curve to go to a trap point. Okay? And this will give you an infinite propeller. So how we define it, so we call this gamma, or we define P gamma as the union of the epsilon finite propeller. So what I'm saying by this is that I'm stopping just epsilon before the trap point. And then you have to add two things. You have to add the orbit of the last point. But this, since this orbit doesn't go out, and I want to have the top part also, I will also put the backward orbit of the facing point. So here I add, let's say, two orbits. One trapped in forward direction, one trapped in backward direction. Okay? So this will be an infinite propeller. I don't want to close it. If I take the closure, I will take also the rough cylinder in it. So just to imagine, let me think of the middle annulus. So this is level C equals 0. what you get is a very, very long spiral. So in the infinite case, you get an infinite spiral turning around the red cylinder. And if you think, so I erase my clock, but if you think of the clock like this, and you take some rectangle here, so the intersection with an infinite propeller will give you an infinite sequence of curves that are accumulating on this vertical arc that is the red cylinder between the two special periodic orbits. Okay? So these points have all arc coordinate equal to 2, and these are marching up below the periodic orbit and marching down to the other periodic orbit. So this is not a transversal to the flow. Each pair of points here belong to the same orbit. Okay, so these are the propellers. So let's go back to the program. So what I wanted to do, if you remember, is to follow this cylinder that is between the two periodic orbits that here is cut. Okay? So if I see, here's my rectangle that I will follow all the time, so let me draw it here. This is my rectangle. Inside. Okay. Let me put it here. Let me put the two special points and the vertical line that belongs to the cylinder. And then, well, what I want to know is what happens with these points that get to insertion. So when I get here to insertion, the trace of the rev cylinder gives me a curve that is going from the special point to the boundary of the insertion. So in the entrance of Wilson, this gives me a curve at some point that goes from the special point that I choose to the boundary. And if I assume all this parabolic shape, it will look more or less like this. And I have two of them. I have one for the top insertion and one for the bottom insertion. And these are called gamma 0 and lambda 0. Okay? So as I flow these curves inside Wilson, these are points that, except the last point, are bigger than 2, so I would know that they will all get out of it. Okay? So these curves give me two infinite propellers that belong to the flow of the cylinder. So if you imagine the rev cylinder to be something like this, there's one orbit, the other. This is so gamma 0 tilde, same lambda 0 tilde. What this will add is two infinite tongues that are flowing inside Wilson that accumulate on the same cylinder. That I will just, this is just a diagram. Let me just follow it here and put it here. So how does it look? So these are some pictures by Joss. These are not really satisfying, but they give the idea. So this is a rev cylinder as is embedded in the Kuperberg before the insertions. Okay? So the next thing that we will have to do in a Kuperberg construction is to take apart here. So choose a vertical line, fold it, turn it, and bring that vertical line tangent to the thing that I erased. Not to all of it, just to the middle part. And the same on the other one. So what we had to do is to do this and turn in different directions. Okay? So unfortunately Joss was not able to do that in the computer, but he proposed this. So this is obviously it's not smooth, it doesn't preserve the verticality, but it gives the idea of what's happening next. Okay? So here I have the rev cylinder, and it comes tangent to the parts that are erased of the periodic orbit. And now the two infinite propellers here will come in and start turning around. So there are paste two places are erased, and they cover this thing. and they start turning around. They start turning around, and they will continue turning to infinity. Okay, these are infinite ellipses. So if you think of what's happening in this rectangle, it will give you along an infinite sequence of arcs in the rectangle that I put in the document. So as this propeller turns, and here I have to make this thing turn a little bit. And stop it there. A little bit farther. So what happens here, so if you see the principle, the infinite propeller, it comes in, it starts turning, it continues turning, and eventually it arrives to this point. If it's close enough to the periodic orbit, it will branch. So the principal part will continue again, but since this, if you think of this line, this is the boundary, it's accumulating on this arc. I told you that before. So there's a sequence of points here that will hit the insertions. Okay? So this will give me this part that comes in here and hits the insertion. And when it hits insertion, I hit the insertion in a curve that goes from one of these points to the boundary of the insertion. So it will give me in the insertion some points here and curves like that. As I turn. Each turn will tell me they are climbing up. It's the same points. So by the identification that I'm doing this, they're coming in and I have these curves. Each one of these curves will give me now a finite propeller. Okay? So when I get near here, I will have the principal branch that will continue straight. And I will have a finite propeller that will go that way. But just for a finite distance. Finite propeller. So as I get here, I will have finite surfaces. And as I go down this here, this gets longer and longer because the radius is getting close to 2. And on the other side, you have the same thing. And the same is happening with the top. Okay? So this is the structure of the magnets. So what happens next? So this is, let's say, level 0 is a cylinder, level 1 is my 2 infinite propeller, level 2 is this thing. Well, these things at their time will turn around the cylinder and will hit insertions. So at one point this will start creating their own finite propellers. And we'll start branching more and more. I never have the space to do it, but we'll start doing it. So this is a little bit, this is a diagram that works well for some things, but it doesn't work for something else. All these propellers are more or less the same width. So they don't look like that. They're not getting smaller. They're almost all the same width. Depends just on how long they are. Okay? And so as I get farther and farther in the infinite, I'll get more and more complicated structure on this thing. And and I will also get a lot of curves in here that now they're not touching r equal 2, but they're touching some vertical rays. Okay. So when we finally got a picture of this, we said, well, it looks like a lamination. It's not a lamination, it looks like. Why it's not a lamination? Because even if you see some kind of laminated structure, well, the boundary of this thing is my special orbit, and it's dense in the interior if I have this generic assumptions. So we decided to call this. So this is the construction. So you get 2 propellers, and you have 4 families, countable families of propellers that generate finite propellers, and then more and more families at each level, and this continues forever. So, well, this is obviously not. Then you have to close this set, so you get more. So this is a dense subset of the minimal set. Okay. So we decide to call this a super.
I mean, this is inside the minimal set.
Yeah, this is inside the minimal set in the generic assumption. In the generic assumption, the cylinder is in the minimal set, so all of this is in the minimal set. And the minimal set is a closure of this set. Okay. So we decide to call this a super lamination. It's not a lamination, it's almost a lamination. Okay. So if you take this special orbit away, and also the limit point of this, well, not all the limit point, some of the limit point, you get a lamination with open lips, and we can give charts, explicit charts.
If you do what?
If you take the boundary away, if you take this away, and you take just the flow of the open drug cell, then you get a lamination with charts and everything. But the time you close it, the boundary of your lips is dense everywhere. That's it. Okay, this is more or less what's happening. So in the generic case, this thing that we call the zipper, that's the boundary.
It's like getting old. You get wrinkles all over your skin.
Yeah, exactly. So these things at the end,
Exactly, sí.
they turn a little bit.
Exactly,
and
sí.
very dense
Sí, sí, sí.
inside of it.
Exactly.
And just to finish, well, maybe I will go fast through the definitions. So you can think of the topological entropy of the flow. So the topological entropy of the flow is measuring
Well,
how
I don't really
complicated it
You
is.
have some lamination, and then
Yeah.
you have stuff nearby. What does it look like on the bottom? Draw a little piece.
So a little piece,
Just a little bit.
just a little bit. So what I think is, so my way of thinking is a lot in this rectangle actually. Okay? Because in this rectangle, so let me draw it with
So
a
where's,
little bit more
where's
of.
the zipper and where's the...
So the zipper will be the boundary points of these sides. At the first step, you just have the rep cylinder. At the second step, you get one to each of the infinite. And we just draw 2, so this is a
And those
countable
endpoints are dense everywhere.
formula.
And
Yeah.
Those endpoints are kind of dense everywhere.
Yeah,
You keep
the
getting more and
orbits of
more.
these points are dense everywhere. So what you can do is to think a little bit about what's happening to these lines when you flow them inside. And these lines will give you another part. So it's another infinite propeller that does the other half. So when I do the second part of this, all these points, there is a countable family accumulating here, will get mapped to points in here that are accumulating here, but also to points in here that are accumulating here, and to points in here that are accumulating here. And each one of these points, each pair of these points is relied by some curve. And this will continue again, because this will copy also the yellow line, and then in it I will have another sequence of points. So each one of these boundary points, let's say, of this one observed, has a sequence of points in the same orbit. They're accumulating on the surface. And they're accumulating in this way on the other. This is how it looks.
So you can stratify the minimal set,
Yeah,
but they're not closed sets, obviously.
exactly.
Yeah.
So
you can
it's
stratify it by
two
levels.
stratum. That's two. It has the two-dimensional stratum and the
Exactly.
one-dimensional stratum.
Yeah,
Or-
yeah. You can also stratify like that. There's a two-dimensional stratum, a one-dimensional stratum, and the one-dimensional stratum when you close it, you get it. So just to finish, let me tell you one
The one number.
fun fact about this thing is that, well, you can calculate the entropy of a flow. You can also calculate the entropy of a lamination if you give a pseudo group. So this thing is not elimination, but we have a pseudogroup acting on the transversal. If I take, for example, the transversal that is here, I get a Cantor set of lifts when I close it, and I can describe a pseudogroup that actually has 3 generators. And these 3 generators in this picture, what they do is, if I have, so the intersection with this rectangle gives me lines in here. So
There is an associated pseudogroup that
There
describes,
is
that
an
describes the
associated-
dynamics?
that describes the dynamics. Both of the, so we have 2 pseudogroups. We have one for the flow and one for the lamination. They're quite related, but they're not the same. So what the pseudogroup does is that let me either go in front, either go this side, either go this side. So this is my pseudogroup of lamination. So if you compute, so the flow has topological entropy 0. You can either do the computation by hand. You can either use a very strong theorem of Katok saying that if you don't have periodic orbits in dimension 3, the entropy is 0. And
You have to have infinite many.
yeah, you have to have infinite many. But if you don't have it, it's entropy 0. But the laminated entropy of this thing is positive.
What's that? How's that defined?
So that's defined by the pseudogroup. You take the words, so you fix a generating
Like
set. The bicycle G's entropy of elimination. So you take a pseudogroup, you fix a generating set, and then you see the words of length n that are separating points, and then you do exactly the same as with the flow, but just with the n, the length of the word. And so this pseudogroup has positive entropy. It's actually, this can be seen as a resilient lift, where so just for the.
What's the definition of a resilient leaf?
So a resilient lift is a lift that has a loop.
What?
A loop inside the lift. So if you take a transversal and you take the holonomy of that loop, is contracting. And that transversal has to intersect the same lift. That's the definition.
What?
And
It has
so
a closed transversal?
so the transversal has to intersect the lift where the loop lives. And not just at the boundary point, but it's an interior point.
Oh,
Okay? So here if you take, for example, this
okay.
this circle is the loop that you're looking for because it's intersecting all these propellers and it's tracing you so lines are in the middle.
So you have a tracking holonomy.
A
and
tracking
there's another point
holonomy.
of the leaf besides the origin.
Yeah, exactly. Exactly. So this is another way of, so you can either compute it by hand, again, you can say, well, this
So
is
what
a
does
resilient
resilient
leaf.
leaf mean about something?
So resilient leaves imply positive entropy. And I think I will stop here.
And today we have Rechtman from Irma, Universität de Strasbourg. He's going to speak about dynamics and topology of the minimal set of Kuperberg flow.
Well, thank you, and thank you, Alberto. I started doing mathematics here 10 years ago, in Alberto, and then moved to France, where I'm now. So I will speak a little bit about the minimal set of the Kuperberg block. This is a joint work with Stephen Herder. It's a work in progress. I will tell you some aspects of the study we have done in the last few years. So I will start by telling you what Kuperberg proved and how she proved it, and then go into the details of the minimal set and what it is. So what Christina Kuperberg plug is proved is that if you have a closed tree manifold, you can it always admits a non-singular vector field without periodic orbits. So the first remark is that a tree manifold has always Euler characteristic 0, so it always has a non-singular vector field. And the idea of the proof is that if you start with a flow that has a finite number of periodic orbits, you can change it for one without periodic orbits. So if, let's say, I have a periodic orbit, the idea is to do a local construction. So I will choose a point, and around that point I can choose a flow box. And the idea of Christina is to change the vector field inside that box in order that I will cut open the periodic orbit.